Hello everyone. Uh, so as I was telling in the last couple of hours, I shall start damped free vibrations, but somehow because of by taking few more single degree undamped systems, I went on to discuss, and I also mentioned in my last class undamped free vibrations of single degree freedom system. So I have taught it for several hours. I have taught it for 20-25 hours also. But looking at the syllabus content and the time permissible, okay, I wound it up. But that topic is so interesting, and you refer to any book, you will find hundreds of systems, and if you have interest, you can go through, at least solve problems and be familiar with that. In spite of solving many problems of that kind, I am not very sure the one what you face in the examination may not be familiar, and therefore I am not 100% sure that you can rely on that kind of question in the examination. Okay? But we have a topic now, the damped free vibrations, what I am going to discuss. It is much relatively simpler and very mechanical, and substitution kind of problems we are going to have it, and therefore from the examination point of view, this is highly reliable. But to understand this, to some extent at least, you can't be blind, or you don't know that you don't have any idea about undamped free vibrations. If you have that, then you won't be able to follow. Okay, you have some idea, and definitely I'm sure you will be able to understand damped free vibrations. Okay, so as the name says, the systems what we have now are going to have damping. Okay, what is damping? The definition of damping. Damping, as you all know that, damping is basically resistance for motion. Okay, whenever motion is taking place, if anything opposes that, then that is nothing but damping. Say you feel that you are riding a bicycle, okay, so a bicycle on you, though you are moving on a smooth road, and if the wind is so much, if it is opposing you, and you have to pedal so much that you have to put in lot of energy to proceed further. So what is the meaning of that? Air is resisting your motion. That is nothing but air is a damping. So similarly, the kind of systems, mechanical systems, the machines which we model, that we call it as systems. It may be single degree freedom system, or it may be multi-degree freedom system. Okay, so damping is bound to be there in all our real systems. Then when it is not there, okay, when it is there, then why did we study that? That I have already mentioned. The purpose of study of undamped free vibrations was to know what is the natural frequency of the system. Okay, now also damped free vibrations. So any frequency of free vibrations is natural frequency. So the system is damped, the vibrations are free vibrations. So now also I am going to find out what is the frequency. Then what should I call this? This frequency I call it as damped natural frequency. Okay, so but in case of undamped natural frequency, I didn't call it as undamped natural frequency. That is by default. By default, whenever I say that it is natural frequency, it is undamped system. And if I have a damped system, and if I want to talk about natural frequency, then I shall call it as damped natural frequency. Of course, they are related, and what is the relationship between the two, etc. All that we shall study. So we know, we have understood what is meant by damping. The damping is the resistance for motion. Then what are the types of damping? The types of damping in our system, mechanical systems, the machines, types of damping. What are the different dampings we come across? Okay, so very simple question and very common question, and the theory question what frequently appears in the examination, please write it down. State the various types of damping and explain in brief That is a very common question for about 6 marks. Very common question. And part of it I shall discuss. I shall not discuss the full thing. I want you to take it as an assignment question and please write it and make notes for that. Okay? So what is that? State the various types of damping and discuss in brief or explain in brief. Okay, the various types of damping are going to be what we call as viscous damping. The first number one is viscous damping. And number two, what we call as Coulomb damping. Coulomb damping. Number three, structural damping. Structural damping. And number four, so non-linear, it is called as slip or interfacial damping. Okay, for part of the question, whatever I posed and made you to prepare, okay, part of it I have answered. State the various types of damping. These are the various types of damping. Okay, I am not going to explain all of them, so but I shall definitely explain the viscous damping, because this is the one what we are going to discuss in our systems in this course. Viscous damping. So what is viscous damping? I shall discuss it, and all other things, these things you are supposed to prepare it. Okay? I shall tell about this. What is viscous damping? What is viscous? Viscous, the term which has comes from viscosity. Okay? Viscosity. Do you remember what is the definition of viscosity? What is viscosity? Viscosity, we never talk for a solid. Viscosity is something related to liquid or even fluid for that matter. Okay? Liquids, we have viscous fluid, viscous, that's what we say, we keep talking. The resistance for flow, all fluids flow, no? We all know. So for flow, if there is a resistance, and that resistance is called as viscosity. Viscosity is the property of the fluid. Every fluid has viscosity, and by virtue of that it shall resist the flow. Okay, it shall try to resist, it resists the motion of the fluid, and that is called as viscosity. Okay, so probably this kind of figure, okay, say imagine here with this discussion, say I have a fixed plate. I hope you understand. Fixed plate, this plate is fixed. Okay, so I have something what you call as another plate here. Another plate. Please remember, it is not a line, it has a dimension perpendicular to it. Okay, this is fixed plate, this is what is moving plate. We call it as moving plate. So the motion will not happen just like that. So I have to apply, I must be pushing it, no? I have been applying a force F, and because of which it is moving. So this is a plate, and to this plate I apply a force F, because of which this is moving. And in between, what is there? So you have what you call as the liquid is there. You have fluid. Whose viscosity is, say mu. Mu is the viscosity of this fluid. Okay? So I shall not go in detail what is this, what is the definition, what is the unit, etc. etc. Okay? So let me assume that this plate is moving very smoothly, or in other words, the velocity is not very high, and even the liquid also has to move, no? The liquid or fluid, whichever is there between these two plates, any fluid layer, usually we believe that for smooth flow, when the fluid is flowing smoothly, then it moves layer by layer. So I have one layer of fluid, I have another layer of fluid, another layer of fluid. So like that, these will be moving in the form of a layer. Okay, so any fluid which is in contact with the fixed plate, that is having zero velocity. So anything which is moving here, which is moving which is attached to this plate, not any fluid, which is attached to this moving plate, that shall have the velocity of this plate. That means the velocity is varying from 0 to this whatever the plate. If the plate is moving with a velocity v, okay, then the velocity is changing between 0 and v. Okay, how the velocity is changing, that is very, very important. It may be smooth, say a straight line variation, or it may vary something like this, whatever may be the variation. Say this, let me assume that this is the velocity. So in this way it is varying. So this is the line. Say here the velocity is 0. So what is the velocity at this distance? That is nothing but this is the velocity. So if I move like this is the velocity. At this top plate, this is the velocity. This is what I mean by v. So it may be a linear also, depending upon what is the fluid. Okay, this is what we call it as the velocity variation. Okay, so now this is mu, this is velocity variation. Okay, why I am telling all this? So I am not taking you to fluid mechanics class. So definitely you have come across this kind of discussion in your fluid mechanics class. Okay, so now you have something what is called as Newton's law of viscosity. Newton's law, what does it say? It says as tau, the shear stress anywhere. So as I said, one layer is moving another layer. There is what is called as the shear stress between the layers. That is shear stress, I call it as tau. Tau is proportional to R. Okay, tau is equal to. So what is that? It depends upon the velocity gradient. Okay, the velocity gradient. So if v is the velocity, okay, so v is the velocity at this end. So this in general I call it as say u is the velocity. Okay, at if this distance say e is equal to say t, and let me assume that this is my y-axis, then this I call it as du divided by dy. Okay, the shear stress is directly proportional to the velocity gradient at what rate. So if I want to know what is du by dy at this point, what should I do? I should draw a tangent, then find what is the slope of that. That is nothing but du by dy. Okay, so therefore tau is equal to what is mu into du divided by dy. This is the velocity gradient. Okay, so tau is nothing but the shear stress. So I would like to know what is this thing. What is the shear stress at this level? So in that case, what is tau? Tau here at this. This is equal to mu is mu. And what is the velocity gradient here? The velocity gradient, as I know that the velocity is v, and divided by, and what is this distance? That distance is what I have called as t, mu into v by t. So as I know that tau is equal to, what is shear stress? Shear stress is equal to the force, whatever you have applied, divided by the area of this plate. The bottom area of this plate, this length multiplied by whatever is the dimension, that will give you what is the area. F by A is equal to mu into V divided by T. Or in other words, F is equal to mu into A divided by T, this into V. So I have put some terms within the bracket here. The idea is that for a given case, for a given fluid, mu is constant. Mu is not varying, whether mu is here or here or here, its viscosity remains same. Then the area of the plate remains same. It is not going to change. After some time the area is changing. It is not going to happen. A is also constant, and this depth also will remain constant, T. So how much depth of oil you are going to have, that also is constant. That means this term is constant. So therefore I can say that this F is equal to this whole thing I am going to call it as C. C, I am going to call it as coefficient of damping. Coefficient of damping, this multiplied by V. So therefore, I call it as F is equal to, in my case, C, and velocity I shall replace it by what is called as X dot. So that means this force, what is this force? The force, okay, this is nothing but the damping force. The damping force is equal to C into X dot, or damping force is directly proportional to the velocity. Okay, and the viscous damping is also because of the friction between the two layers of the liquid. So this also is called as liquid friction. Viscous damping is nothing but the damping because of the friction in the liquids. So that friction is called as viscous damping. And because of such a simple relationship between the resistance force and the velocity, we have so simple relationship, and because of this, in all our discussion, most of the vibration discussions, they will have only viscous damping. They assume that the damping is viscous damping. Then, as I said, the damping may be this damping. This damping is Coulomb damping, is also known as dry friction damping. So you have a solid surface, another solid surface, and they are in contact. There is relative motion. You all know how the friction laws. So friction is a must. So there are so many such parts in our machine, and we are going to have Coulomb damping and other dampings also. All the dampings is possible to study. For the sake of study, all these three dampings can be replaced by what is the equivalent amount of viscous damping. So therefore, whatever may be the nature of damping present in the system, it is possible for us to find out what is the equivalent amount of viscous damping, and hence always we are going to take what is called as viscous damping. Okay, so we have understood how the viscous damping works, etc. Now, how it is going to be constructed in our system, how we are going to represent it. In our mechanical systems, we are going to represent something like this. We have a piston, and we have what is called as cylinder. This distance is equal to this distance. Please adjust it. You have a piston, and this cylinder is closed. You have oil here, full of oil this side and also this side, and there is a piston which goes through. Okay, you have a oil of viscosity mu. Okay, let me assume that this is having some distance. Okay, some distance, say, let me call it as n. So let me call that this dimension is A. This dimension is, let me assume that this dimension is D. And let me assume that this dimension is, okay, what is called as RC, radial clearance, something like that. Okay, I have this. Okay, this thing, the piston, along with this piston rod, so there is a solid, there is no relative motion between this. So this may go up and down. When this goes up, the oil from this side will start moving this side. And this piston goes down. Similarly, the lack of space for the oil, this oil has to rush here. So therefore, this becomes, please understand, this portion is our moving plate. And this one, this is our fixed plate. And this is what is in between. In the previous diagram, whatever I had shown as some T is nothing but RC. Or in other words, what was C? C is equal to mu into A divided by T. I hope you still remember this. This was our diagram, and this was our T, and this is a plate, moving plate, the area of this is this, and mu is the viscosity. Okay, so here in this case, so if I apply this now, mu is mu only. So A is what? A is the area of the moving plate. Area of the moving plate. Okay, here what is the area of the moving plate? It is this portion. Please remember, it is not only here, it is all surrounding. It is a circular in nature. That area is nothing but pi into d. That gives you me the circumference multiplied by this distance. So that pi d into A, this is nothing but A, divided by T. T is the gap between the fixed plate and moving plate. Here this is the fixed plate, this is the moving plate. What is the gap? The gap is RC. So this value E is what is called as C. Okay? So for any damper, this is what we call it as dashpot. This is called as a dashpot, which indicates the viscous damping. So dashpot, for any dashpot, this is referred by what is its coefficient of damping. So that value C is equal to mu into pi into d into A divided by RC. For a given dashpot, C value is constant. I hope you understand. So now onwards, okay, this we shall have, will not have so big. And in short, this we are going to represent it something like this. This is how we represent it. Sometimes we may draw a line here or you may not have it. It doesn't matter. This is what we call it as dashpot. Okay, the viscous dashpot. So I hope you will complete the remaining things and prepare notes for this. This is what I mean by types of damping, and you have understood what is viscous damping. How do we indicate viscous damper or what is called as dashpot? Okay, so now how the damped system looks like. Damped system of single degree of freedom system. What shall be the components? Spring will be there, mass will be there. Now we have a new component, what is called as dashpot. So the system may look something like this. So I have a spring, and spring and dashpot are always parallel to each other. This is a dashpot, and we have attached a mass here. So this is the simplest spring mass dashpot system. This is called as spring mass dashpot system. This is the meaning. So our system of study is going to look something like this. Okay, we have a damped system, and that system is going to be spring mass dashpot system. I hope you have understood this also now. This also is good. Now the next one, what I intend to discuss is what is called as undamped vibrations, of course free vibrations, versus damped vibrations. Damped free vibrations, of course free vibrations. This free vibrations is applicable for both cases. Okay, this is applicable. Okay, so now I would like to discuss this and this. Okay, the first thing I can say that these vibrations are also free and these vibrations are also free. And immediately I can say that the system is undamped and the system here is damped. So this is how the damped system, and let me draw the figure for undamped system. This is how the damped system looks like. This is M. So this is a M system, spring mass system. This is spring mass dashpot system. Okay, so undamped, fine. Okay, now what happens? So to start the vibrations, free vibrations, what I do? I pull this mass and pull it up to here. Okay, what I mean is I apply force and have some displacement and leave it. Okay, then this mass will go on oscillating like this. So why does it oscillate? Just because when I pull this mass say up to here, I have done work. Work has been done. I have applied force and also displacement has taken place. Force multiplied by displacement is the work. That is nothing but the energy which I have pumped into the system. So similarly here also, if I want to start the vibrations, I pull this mass here to here. That means here also I have pumped energy into the system. Okay? So in this case and in this case, the difference is here I don't have any damping. That means nobody is resisting the motion. Okay? So therefore, whatever the energy was there, and that much energy will be there all the time. So therefore, these vibrations shall go on forever. There is no loss of energy. But what about here? Every moment, every motion, there is a continuous opposition. Okay? So there is a continuous opposition, and therefore, whatever the energy you have pumped in now, there is a continuous dissipation of energy. There is loss of energy. The damping, what is the meaning of damping? The motion has to take place against some force. That means some extra energy you spend, whatever the energy the body is having now, that energy is spent in moving further. And this energy, what you have at the beginning of the opposition, and slowly your energy becomes less and less and less. Sometimes finally it becomes zero, and you don't have energy to have vibrations. So therefore, the vibrations forever, vibrations here forever, all the time in the undamped vibrations, forever, as no loss of energy. But here vibrations, I have a condition, if at all are there. So what I mean is, sometimes I put this mass, I have pumped energy and leave it. That energy may not be sufficient to have vibrations. So when I leave it, then this mass may go back and may comes back to the equilibrium position and stops there. It doesn't go beyond that. If the mass goes on either side of the equilibrium position continuously, then only we say that we are having vibrations. That is why, if at all are there vibrations, if at all are there, shall die down soon. That means you will not have vibrations. You will not see vibrations forever in case of undamped system. I hope you understand. This is how the difference between undamped free vibrations and damped free vibrations. Okay, then what is the purpose of study of this? So as we know, okay, I said the vibrations may be there or may not be there. So that part also. So it all depends upon what is the value of K and C and M. They will decide whether vibrations are going to be there or not. So under what circumstances we have vibrations, and under what circumstances we are not going to have vibrations, that also we are going to study. Okay? If we are not going to have vibrations, then we are not going to discuss that much, because our purpose of study is to study vibrations. Therefore, so under what circumstances we have vibrations? Okay, then vibrations are there. It is moving like this, and after some time it becomes zero. So that means every time, so this is what, from this question I am going to the one extreme question. What is this? What do you call this? This is called as amplitude. Amplitude is the maximum displacement on one of the mass on one side of the equilibrium position. That is amplitude. So in case of damped free vibrations, the amplitude of vibration is continuously decreasing. And in case of undamped, the amplitude will never decrease, amplitude will remain same all the time. Here, the amplitude of vibration is decreasing, and there is a definite rate at which it is going to decrease, and that we are going to call it as logarithmic decrement. So our purpose of study is also to know at what rate the amplitudes are decreasing. So therefore, there is a difference in the study of undamped systems and this. In undamped system, the amplitude is not changing, so therefore that part was not necessary to study. So our aim was to study only the natural frequency. What is the natural frequency of the system? So therefore, the system, set the free vibrations, write the equation of motion, and write what is the natural frequency. That is the end of study of undamped system. But here it is not so. Here also we set free vibrations, we write down the equation, then we write down the solution of it, and then we also make a study. There the study doesn't end. That is the beginning of our study, as I want to know after how much time it is going to come to rest. At what rate the amplitude is decreasing. Therefore, the study is not going to stop once I write the equation of motion in case of damped free vibrations. In case of damped free vibrations, in fact, the study is going to begin from there. So, write the equation of motion, and from that you write down the solution, and you check what is that, whether you have vibrations or not, etc. And that's what we are going to study under what is called as damped free vibrations. I hope you have understood, you have some idea. Very interesting topic, relatively much smaller topic. Probably in 3 sessions or 4 sessions, I wish to wind up this topic, and that is how this module can be completed 100%. Okay, all the best.